Hello, this is our presentation on the chest X-rays classifier with deep learning with my teammates Dan and Ksenia. And without further ado, let's go to the next slide. So our project focused on classifying multiple pathologies in chest X-ray images from this NIH database. The chest radiology remains one of the most common diagnostic tools in medicine, and it has an increasing workload on radiologists, meaning there is a very real need for automated, accurate screening methods. Our project aimed to develop a CNN, a convolutional neural network, that can identify multiple diseases such as like cardiomegaly or pneumonia in new and unseen images. So the NIH Chest X-ray dataset, comprised of over 100,000 images, gave us an excellent basis for training and evaluating our models, but we'll dig more into the pre-processing in a bit. But ultimately, we were envisioning an AI-assisted tool that could highlight suspicious findings and help radiologists work more efficiently and potentially improve the patient outcomes. Cool, so a bit of the background. The idea of using deep learning to analyze these medical images is not really a new idea, of course. There's research groups that have shown that CNNs, especially those adapted from like ImageNet or pre-trained models, can match and even exceed the average radiologist performance in certain tasks like pneumonia detection and chest X-rays. Clearly our use case here. These CNNs are very well suited for these image-based tasks because they can automatically learn these feature hierarchies, which eliminates much of this like manual feature engineering typical of the traditional models. So we took some inspiration from similar medical imaging projects, like ones that were for like skin liaison detection or diabetic screening, and we applied similar deep learning frameworks to these chest images. By leveraging that strength of CNNs, our solution aimed to systematically identify and distinguish multiple pathologies in a single image, offering a potent tool for medical practitioners.
For the dataset, we're using National Institutes of Health publicly available chest X-ray dataset. It contains X-ray images, corresponding labels, as well as important tabular data such as patient age, patient gender, follow-up number, view position. Tabular data matters because, for example, X-rays for male and female patients would differ. Each image in the dataset can have multiple labels such as atelectasis, emphysema, pneumonia, and other medical conditions. We wanted to produce a classifier with a broader usage, and we grouped our target labels into wider categories: cardiac issues, fluid-related issues, hernia, infection, lung-structured issues, no finding, nodule mass. No finding is important since we wanted to have accurate predictions for patients without findings on X-rays. The dataset naturally contains class imbalance, which we addressed during training with different approaches. The model architecture that we selected is hybrid and includes two branches. Image branch uses CNN to handle X-rays, and tabular branch uses dense network. Next, I will do a short live demo of the notebook with the model's code. Here is a notebook connected to a powerful H100 GPU-based instance. The first thing I wanted to show you here is our model design and building. We have an image branch and we have a tabular branch here, as well as the fusion branch that concatenates those branches. And for the output, we use sigmoid activation function to output probabilities for each class. Here we just plot out images with the labels to make sure the data looks good for training. And during our training, we monitor the model loss as well as other important metrics such as area under the curve, accuracy, precision, and recall. This notebook is for 7 classifiers doing combined work, so here is the final classification report that shows results for each class. Some notable challenges during training is addressing class imbalance and model performance improvements. We don't want our classifier to mimic probabilities for each class occurring in outputs. To address the class imbalance, we use a custom loss function for multi-task classifier, and we separately created an approach that trained 7 individual task classifiers on fully balanced data. Single task classifiers demonstrated better learning ability as well as more balanced results for precision recall. Multi-task classifier captured better information about medical condition co-occurrences, but showed overall worse results. When optimizing for accuracy, we explored pre-trained models that demonstrated better results overall. So overall recommendation here is to utilize pre-trained models specialized in medical imaging, such as Red ImageNet.
Hello, I'm Daniel Arde, and I'll be presenting on our fine-tuning of EfficientNet. So what is EfficientNet and why did we choose it? EfficientNet, originally developed by Google, is a CNN architecture that scales with depth, width, and resolution in a balanced way. It's known for achieving strong accuracy with few parameters compared to alternatives like ResNet or DenseNet. Prior research on chest X-rays and medical datasets has shown that it's consistent performance well for multi-label classification tasks. And we also chose it because it's efficient. It has a good performance to compute ratio and strong results in similar studies. Our architecture, which you can see here on the right, removed the original classification head and added global pooling, a dense ReLU layer, and a final signal output. These changes were basically just so it would fit to our 7 classification model. We evaluated our final EfficientNet model on a holdout test set of 4,927 chest X-rays labeled across the same 7 diagnostic categories as our other models. After applying per class thresholds, the model achieved macro F1 of about 0.43 and a micro F1 of 0.47 and a micro recall of 0.7. Recall is really important in these medical cases because essentially when you're building a model like this, you want it to be a little bit overly aggressive with making diagnosis. The thinking here is that if a medical professional looks at something with any testing, it's much better for the test to come back more on the aggressively diagnostic side than on missing a key diagnosis. Imagine if you go to get a routine test results and the risk of the test results being negative could cause you to go on your day living with a critical condition. So as with all medical pathology, the thinking here is we optimized our recall to be as high as possible for EfficientNet such that it could always make sure that it would not miss anything and that a medical professional would review or order more tests, follow-up tests to figure out what is or is not important to diagnose. So with both our models, recall was really important here, and you can see on the left here are the overall results. Pretty good results for EfficientNet, but a few of the minority classes struggled. So with future trainings, we would probably try to optimize here. On the right, you can see an actual demo of what this looks like. So this is an actual demo of EfficientNet labeling a thing, at lung X-ray. And you can see actually, if you look at the lungs, there's actually signs of pulmonary infection here, probably consistent with something like pneumonia. So this perfectly fits under our infection infiltration class. And just to reiterate, those are the white lines there. So in conclusion, between the two models, EfficientNet offered stronger generalization and better overall recall after threshold tuning. The custom hybrid CNN model allowed us to inject patient metadata and performed well on certain classes, but lacked consistency. Our biggest takeaway, threshold tuning made a dramatic difference, boosting some F1 scores by more than 2 times. Going forward, ultimately, our goal is to build a system that would flag subtle findings early, helping radiologists and other medical professionals focus their attention where it matters most. Experimenting with the model and our CNN and our fine tune, we would probably try combining these into some full hybrid model where initially EfficientNet may additionally identify things, and then we'd have a later CNN that incorporated the tabular data. We would probably evaluate generalizability on external data sets beyond the NIH to reduce the dataset bias. We'd also probably improve label quality with manual audit or even semi-supervised refinement, probably with medical professionals like radiologists. And we'd also probably develop a clinician-facing prototype with a review flag system for high recall alerts. Basically, that just means that if we find any real issues where it's flagging things way too high or it's completely missing conditions where there would be a human in the loop kind of feedback. In the sum, I think if we were to explore regulatory requirements and performance monitoring for potential clinical deployment, we could have a successful model here that could really help identify key issues in the lungs early, leading to overall patient success and health. Thank you.